Alright, so we're going to talk about competition. This is my first online lecture, and well, I did record several times and it was not succeeded. So this time, let's give it a try again. Right. So, well, the rest of the semester is going to be look like this, I guess. Let I keep you update on if there's a change or anything. I'm not sure yet. How we going to handle the finals and so on. So we'll look into that and keep you updated. Right? Okay. So right. So this model simulation that we're going to look at is competition. It'll be different, a little bit different than what you have done so far up to midterm. So we did a lot of equations related to physics, right? And so the most people who found it difficult will have a little bit relax the comfort zone, that you move into a little bit comfort zone when you're looking at the rest of the models that we're going to simulate. Okay, right. So this one is called competition, and we are looking at uh, how the species compete each other, and for limited resources, of course, and how that going to apply to the Vensim and simulate that. Okay, right. So saying that, about little remarks on midterm, most of the people did very good. Well, the I think one third of the class already have A's, so that's a good thing. And yeah, of course, I have done 5 point curve. So with that 5 point curve, I think three or four people got full marks, like 100, right? And well, I have to grade a few papers. So I will do that. I had to collect that from the office, and then I'll do that, and then I will post the statistics on how the people did on the midterm. All right, right. So put that aside, and if we're talking about the quizzes, well, of course, I'll let you know. We have four more quizzes to go. How are we going to conduct that? So I'll let you know on that. Okay. All right. Okay. So back to competition. Um, so there are a few terms that we have to look at. What is competition, and what are the categories we're looking at? So let's start this. So the first thing is the competition. What is competition is? Well, well, when we're talking about competition, uh, there are two types that we're looking at, right? The first is, we say, the struggle between individuals of a population, or between species of this of different kinds, fighting for the same limited resources. So what does this mean? So the good example that come to my mind on this one is, these days the people fighting for toilet papers. Yeah, right. Yeah, you have seen that in some media. I have seen this. So that is one good example that everybody can remember. So that's why I just picked this one, right? So there are two people fighting for the same limited resources. So these days, the toilet papers are limited resources. Not many people uh, find it in the shops because it's gone actually. So so the compete. So this is one which is, we can say, the struggle between individuals of a population for limited resource, or limited resource, or the limited resources, you can say, right? So this is what it is. So in this case, yeah, oh, you can see, so this is valuable thing for two different um, groups of same species. So you can say, well, you can say the individuals of a same population, right? So it's a good one example. So the other one I can say is different species, like let's say you can take so the one of the things that I can talk about is the hyenas, um, and let's say there's the hyenas and then the lions of in Africa. Uh, let's say this is a lion, right, fighting for same little things like deer population or something like that, right? Right. So two different kind of thing species, right? Fighting for one little thing, which is it's like that, right? So you can say between species for the same limiting resource, right? So that's the other example I can give you related to this. So this is what is competition is either it can be the same population or it can be different species fighting for limiting resources. So let's move on and so interspecific. So what does interspecific means, right? So the interspecific is a competition occurs between the population of different species, right? So you may uh, keep mind. I think I missed one here. Yes, the intraspecific. That's what we had to talk about first. Uh, so this is what we just the same example of a human fighting for the same resource, like kind of thing. Uh, well, when you're talking about intra-specific, the competition, so that is internal thing, right? So that's why it's called intra. So keep your mind on this word right here, intra-specific. Okay, so that means that is internal, right? Within the group. So that's what means within population, right? Okay, so the same species that means. Okay, so when you're having the fight for the same things, so the competition on this kind of competition is very familiar for everybody. I know, even you have a game, you have you fight for the win, right? So it's kind of things like that, but any kind. So this one, if you say intraspecific, that is the competition, right? The competition we're looking at here is for the limiting resources, right? That is only for this kind of model, but competitions, when you're thinking of a competition, it can be tangible, intangible, more than resources. It can be something else as well. For example, I can give you you competing for a win or the glory of something that doesn't have the resources, but it is just the satisfaction, right? Yeah, uh, human do that, right? And I don't know the animals doing that. Hmm, not sure, right? Maybe, right? But anyway, for the glory, that is something different than what we're talking here. We only focus on the limiting resources in this case. So the intra-specific means you fighting within the same kind. Okay. So the next one is the one which is interspecific. So the interspecific means, of course, you have two different species or more than that, and then you guys are fighting for one type of things. So this is much more into uh, everything the out there, which is if you have, let's say, uh, the best example given here in this lecture is you have one type of fish. So this is about little fish which is in certain area, okay, and you have two different big fish, right, and in the different types of them. Want to want to uh, have them as their food source, right? So their survival is depending on these little fish right here, right? And so both of these two big giants fighting for um, this little fish right here, right? And if one of them eat a lot, the other get less. That's what the idea is. Okay. So talking about this, this is what we're looking at the interspecific um, competition. Okay. All right. So let's move on. The other one is interference. So the interference is again we can go to the first example we were talking about, which is right. So you have one person here, right? And he's taking most of the toilet papers, right? The other guy is also fighting for that, right? But he's not getting much, so this one get more of it. Okay, so this means one species interferes or not letting the other one have it. Okay, so that kind of thing is called uh, interference. So yeah, of course, eventually this one will have more of these, right? And the other one will have less because one species is dominant here. So this is what the Charles Darwin says: survival of the fittest, right? So when you're having something like this, so the one person is collecting all from the other, right? So this is the stronger one and this is the weaker one, right? So this is the stronger one and this is the weaker one, right? Okay. So this will lead into something else. So this is a direct interaction between two individuals or the species where one is not giving the other. So if he pulls, he will lose. So he get more. This one get more and this one get less, right? So in this case, so that's what the interference means, right? Okay. So this interference causing a lot of problems, right? The next slide we're going to look at what are these problems, why, what matters when this happens, right? Okay. So when this happens, this thing happens. What happens is it will cause a resource depletion, which is nothing but so we have one collect more from the other. So again the toilet paper example or the food, let's say food. Okay, so let's say this is apple, that is all human eat apple, right? And then this guy get more apples, right? So this is apple right here. So now they have big buckets of apples, right? And he collecting more. This guy, well, he's too weak to get apples. So in this case, he don't have apples much. But the other one get more apples from here, right? So, well, obviously, one person will get really happy on this, right? The other one gets so sad on this, right? So this one is sad, this one is happy, right? Um, right. So this is what exploitative, or we can say exploitative, or the resource depletion. Individual reduce the available of the resources to the other. So what happens when this happens? When this occurs? Well, the problem here is, well, these guys don't have food. So what we have to do, either they have to travel far to get food, right? They have to travel far away to get food. But on the other hand, these guys don't have to worry about that because they have enough resources. They're happy and they can spend that time to manage their lives better, right? So in that case, when you having that kind of situation, these guys will move far because that means they have to spend more time on finding food, while the other group has more time to have good life. So this will cause them to have uh, more long life, right? Long life, and then also increase in population, right? So because they have more resources. In the other hand, if you don't have food, of course you die, right? So there will be less reducing the population on this. They get sick because they don't have enough nutrition, and whoever has strength will go far away and bring food, but the others will uh, die without food. So this is a scenario which is of causing by resource depletion, right? So this is the case of resource depletion of if you're thinking of a competition of two different species. So it is an inter-specific situation, right? I mean, we're going to look at the inter-specific situation of this, but what I've drawn here is intra-specific situation of resource depletion, right? So if you're talking about human, of course, right? So I mean, the picture is showing the intra-specific. That's what I mean. Right, so let's move on. In this case, we are going to look at interspecific, which means two different species in the same area fighting for same kind of fish. Right, right. So, as a little image on this example is you will have little fish like this, right? Let's say you have fish like this, a little fish, and then we going to look at a shark, right? And we call this kind of sharks white tip shark. The other type we're going to talk about is called uh, black tip sharks. So these are black tip sharks, and they all attacking these fish in the area, right? So then, so how does this affects on their population on both? So that's what we're going to look at. Right, so this is a limited resources, right? And then these guys want part of it. These guys want a part of it. And then these guys want a part of it. So how does that affect on their population? So this is what we're going to model. It's a funny thing that we're going to model actually. It's very interesting to look at it, right? And see how really going to simulate this, right? Okay, so let's move on. Right, so in this one, this is you may recall these equations from the previous lectures, so I'm not going to go deep on this how you get the analytical solution. You did this on your exam as well, this part right here. And then so let's talk about this a little. Here the birth proportional to number of individuals. Of course, that's the first thing we did in unconstrained model, right? So we said the population is proportional, right, to proportional to we said initial population or the previous population, right? So it is proportional to the previous population, right? Yeah. And then we said okay, so if that's the case, so we can put some equation here, right? So this is initial population, so that means a constant time, right? Constant time the initial population. So this is we call R1. So I put P0 here. I put P0 here because that's the previous population. Okay, so again for the deaths we can say the same, right? So for the deaths we say All right. The population of uh, deaths, so you can say D is proportional to the previous population again. So of course you have to have the previous population to calculate that. And this means D is equal to constant times the previous population, right? P0 in this case. So this means what? So if we consider change in population, right, it's going to be equal over time, of course, it's the rate over time, is births minus deaths, right? Yeah, so we know that already. Okay, so in this case, what? Well, in this case, we can write that again. Uh, we can write this as births is nothing but R1 P. Let me put P0 again. So that's what I wrote there. Minus R2 P0. So this is the same thing as we can write as R1 minus R2, right, into P0. Okay, because the P1 is P0 is common, so I just took it out like that. Well, so here the analytical solution of that is written by the P is equals P0 into e to the power, well, instead of previous values, so we have now R1 and R2, right? R1 minus R2, R2 into T. Oops. Well, that is the equation here. Well, it seems like I wrote out of the screen, but anyway, so this is the equation right here, right? So that's what I'm talking about. Okay, so how we get this one from, I mean, how we get this from here to here, right? That is what we did in a even exam. We take the derivative of both sides, and then we get the exponential value on the both sides, right? So you remember how we did that, right? Okay, so I'm not going to go there because that is the previous lecture's analytical solution will be, only difference is instead of r that we have here is r minus r2, right? R1 minus r2, right? So that's the only difference. Right, so let's move on. Right. And okay, so on the change in depths in here, we have another equation. That's what we're going to use in this. So that's why I'm not following the previous slides much, because this is what we're going to use for most of the equations. I mean the equation that we are applying for our simulation. Okay, so so here the competition may cause change in the number of deaths. So this is the number of deaths that we are analyzing here. Um, as I said before, when you're looking at two different species, right? And like I said, okay, so this is, let's say, this is your black tip sharks, right? And you have more black tip sharks here, right? And so this is BTS, and they eat a lot of fish. Let's say they eat a lot here, right? Again, and when they eat a lot of black tip sharks, right? Black tip. I mean, if the black tip sharks eats more of these little fishes here, right? The white tip sharks, on the other hand, uh, so they are skinny. They don't have food, right? So this is the white tip. They are small because they don't have much food, because these are black tips are big and then eat more. So that means their population is going down, their population going up, right? As I said, well, if they have enough resources to survive, they don't have spend much more time. They don't have to. So they have a good time. And these guys are have to search food everywhere. They have to move on because of that their population is declining, right? So that means what? One population, the cause of one population is affecting the other population. So this population is caused by decline of this population is caused by the increment of this population. So if they increase their population, they eat more, right? Yeah, obviously that's the case. So if they are eating more and more, if they need more and more because their population is higher. So in that case, if the black tips are eating more, white tips don't have much chance to eat a lot, right? So that will cause a problem to them, right? So then that means what? The white tip sharks will be the population of white tip sharks will be decreased very seriously, right? So that's a problem here, right? Okay. So so because that means the death rate of a WTS well depending on so this is what they come up with depending on this situation in this story behind this story what we conclude is the change in deaths of one species is proportional to the multiplication of both species. Okay, right. So what is W? What is B in here? Well, we say the population of BTS is B, population of WTS is W, right? So it says right like this, right? And then, so what is this? Is a proportionality, right? This is a proportionality. So how do you change the proportional to the equation? We can say D is equal to constant time. Constant time, so let's say in this case a constant C, W, BW, right? So this C value will different from for the change of depth in WTS and the change in depth of BTS. So that is a little different. So this C, this is just what I wrote here. Right here is just a common equation for both, right? It doesn't matter you multiply B by W or W by B, it's the same thing, right? But the constant value right here, the constant value right there is different from both ends, right? So different species. Well, so those are the things that we have to consider in this case. So where the W is the depth proportionality constant for the WTS. So the symbol B is the depth proportionality constants for B. But both of those are in the equations you can say is equivalent to the multiplication of both populations, right? So that is what we are looking at here. Okay, so how are we going to apply this? So this is one review question here. So we will look at the review questions and analyze this. So one it says let W be the number of white tip sharks and B be the number of BTS, which is a black tip sharks. We simplify this model assuming unconstrained births. So that means there's no constraint, so there's no deaths in this one. That's what it means, right? Yeah. And after completing this question and before continuing to the text, we suggest you to develop a model. Of course, they're asking to build the model after this. Okay, so what is this? Give an example of the births, the equation for this, right? So in this case, the birth equation is nothing but what? So we can look at this one as so the births we can say well So the births of the population, or whatever we can say, population, right? So equal to, right? Oops, the population is equal to some constant time the previous population. So that's what it is, right? Okay. So, but the deaths in this case, you may have to apply. Uh, so you may have to consider the population of the other the part of it, which is nothing but the population of black tips will cause the deaths, right? So it is also include the deaths part. Let me write it like so. The death equation. Let's say let's uh, let's write it as D is equal to nothing but it will be proportional to the multiplication of B population and the W population, which is a black tip sharks population multiplied by white tip sharks population. So again, the death equation is equal to constant time W, the BW, right? So this is how when you're going to apply this is how you're going to apply the equations of answer. So this is one right here, this is the other right here. So when you apply these two, uh, you can see how the behave of the simulation. So let's move on. So this is one kind of a review question. I hope you understand that. So the birds is totally different. When it comes to deaths, of course, the other population or the type of species population matters because of what? Because of the limited resources that they are sharing in the same environment. Okay, so the review question 2 is asking if all other parameters are equal, uh, the WTS death proportionality constant, which is W, is larger than the BTS proportionality constant, which is B. Which population? So the which one is larger now here? The death proportionality constant of white tip sharks is greater, right? And the death proportionality constant of black tip sharks are less, right? Which population should be larger after few steps of uh, time? So what is the actually what does this means? So one, it means the change of depth of white tips, right? Is if you say W P W, and this is for the white tips, right? And the other one it says change of population for P, the black ones is this, right? This is the big W, obviously. This is the big one, big W right here, right? And this is for the BTS, right? And so they're saying this one is bigger, this one is smaller, obviously. If this is the same value and this one is bigger, that means obviously if the if if this small w the constant is big, that means the deaths are higher, right? So this guy is dying more, this guy is dying less. So that means what is it means? That means which population is larger? Obviously, the WTS population is larger because they have less deaths, right? Yeah. So these have higher deaths for the WTS, and this has less deaths. Okay. So why? Because these two values are common to the both, right? It's a multiplication of the same population. So in that case, this constant matters to decide which one have more deaths. So if it is more deaths for the WTS, well, uh, let's deaths for BTS. So in that case, the answer for this question is BTS, right? Okay, so that's the answer for this question, right? Okay, so move on to the rule of thumb. So this is something very interesting. The constant proportionality for product of populations such as BW is frequently at least an order. So what this means is the proportionality constant for both of them when they're talking about the population growth or anything like that. Uh, Always has to be less than. For let's take an example. So the example that we have in this chapter is saying, I think the BTS is 15, I guess. Yeah, let me check. 1 minute please. So I think in this example on this chapter they're talking about, yes, BTS is 15. So at the beginning, let's say you have 15 here. Okay, and WTS is 20. Let's say 20. WTS is 20. Right. So this is 20. And so if you have initial population like this, let's say your birth is just one, right? Okay, one per month. So that means each of these have 15 by next month. These ones have 20 by next month. So whatever, whenever you calculate that like that, so uh, if you have the constant of death constant of 1, right, proportionality constant of death is 1, what that means is the total population here is 15 and total population is 20. But if your death constants or the death population, the proportionality constant, if it is 1, what's going to happen is if you multiply B by W and I mean the big W here, and you multiply that by 1, right? If you call this as the death, right, change of death or the death equation, this will give you what? 1 multiplied by 15 multiplied by 20. What do you get? 300, right? Is that so? If you have this one more than 1, right? That's not, that doesn't make sense, right? Because let's say this is a white tip sharks, right? WTS death. So total WT is anyways 20, and so the deaths will give you 300, right? Uh, that does not make any sense. So that's why it says the decimal point move to the one place on the left when you're talking about these kind of things. So that means that proportionality constant has to be very less value. Okay, so that is something that you may have to consider. So this is what it explains here. Uh, I mean, they have a little paragraph discussing this issue. If you did not understand what I'm saying, just go through that lecture notes. I mean, in the book, they will have more explanation for this. So obviously, if you have this kind of a population, so 15 of these and 20 of these, and if you put that in the death equation with a constant value of greater than 1 or something like that, uh, doesn't make any sense because it will come up to 300, right, or more. So the deaths, it will be extinct of this WTS in the next timestamp, so it is not really make any sense. So you may have to be careful when you're applying the constant values. So that's what it means. Okay, right. So then the last thing on this lecture is we're going to look at uh, this little chart here. I mean, this is a Vensim simulation. You can see how that behave on this graph right here. Before that, let's go through this equation. When you it's the same thing that you put I mean apply on your homework, of course, that we had some uh, the homework we have equations, how we learn how we apply the equations and so on. So this is the initial value for one type, and then the birth fraction here is, this is the birth fraction we given as 1, right, in this case, right? And so the births will be nothing but the population into birth fraction, is we call it birth. So this is the same thing that we learn as equals to rp0, right? So initial population, and the death proportional constant, you can see here, if this is 1, you give this one as 0.2, right? So you see it's just less than 1, obviously, right? Otherwise you won't get the right values. Okay, so and then so this is what the rule of thumb explains in the previous slide. And here, so the BTS deaths is going to be equal to death proportionality multiplied by WTS population multiplied by black tip sharks population, right here, right? So the population multiplication of both populations into the constant, right? Again, for the same thing for white tip sharks, you have initially 20 of them, and then a birth fraction is right here, which is 1, and then also the births here is nothing but the constant value multiplied by the birth fraction, I mean the previous population multiplied by the birth fraction. And again you can see the deaths proportionality is point something, right? And the deaths will be depending on WTS and the BTS multiplication of those two populations into the constant, right? And when you're doing that in your simulation, in the Vensim part, you can see now, look at this part right here. Here we can look at the birth fraction, and so the birth fraction matters to the rate of births, and the death fraction, the death proportionality constant here, right? Death, uh, 1 minute, please. Right, so the death proportionality constant here is matters to the number of deaths, right? So the difference between these two, which is a birth minus deaths, right? So this is what this is, deaths, right? Right, okay. So the birth minus deaths are the one which is filling up this piece right here, right? So that is the difference, that is the actual value. So this is the rate of change of births and rate of change of deaths, and the difference of that will be the population, existing population. And also the same thing that you can draw for the other side, which is the BTS. This is the births and this is the deaths, and the difference of those two will be filling up here, right? So the other factor here is you can see the deaths of this guy, deaths of WTS is matters, or depending on the population of the BTS. So there's the arrow which is going from here to here. That is the equation satisfy the condition of this, which is a BTS population, right? The BTS population matters to the deaths of WTS, here, right? So that's what it means. So that is where the arrow is going from here to here. And also we have one arrow from the WTS population. It also matters to the depth of BTS, right? So that is something that you model this in Avansim. So I think you will understand the behavior or the drawing, how you model your final report, whatever you're going to simulate. You may have to consider these things, and this is how you're going to join those things together, right? And then you will have applicable equations, and then this is how you model it. When you model it like this with the applicable equations, you will get the results look like this, right? So this is the result that you get from this, right? It's very interesting the way it's look like. So you can see here when there's a break even right here, and when uh, the white tip sharks decline their population, obviously the black tip sharks increasing of their population, right? So um, when one goes down, the other goes up. So that behavior shows here um, in this. So you can assume this one is pretty much closer to the real life simulation. I mean the real life scenario of a simulation. Okay, so that is what we're looking into this. Right. So this is the last one, which is showing here is the result within the table. So you can see at the initially at the beginning we had like time 0 the initial population of white tips, initial population of black tips, and then after 1 month this is what happened depending on. So what makes this happen, what makes this changes? Oh, nothing but the little b and the little w, right? The value of those matters to this. So that's all actually we consider in this one, right? So these two values depending on these two values, this the whole table will design like this. So you can change these values and see how these things behave, all totally different, right? So but in this simulation so this is what happens. So this is what actually you have to do in the final report. Of course you will come up with the equations and have a little chart just look like that one that you saw in the previous slide, and you generate these things and see how it behaves and whether is it compatible with your scenario or the simulation that you do, and then you write an analysis of it. So that's what your final report is also. Okay, so I hope you learn new thing about competition. So the next time we're going to look at predator prey model, which is something a little bit different than this one. And right, so I will put another lecture very soon. Right. Okay, so if you have questions regarding this, please email me. I will put a, I will set up a forum if possible, and then I'll let you know how we're going to conduct the office hours as well. I probably go on Zoom and set up that way time available so you can come on Zoom and talk to me if you have questions, right? So that will be something I'm planning on setting up. Okay, right. Okay, so this is the basic competition. So we will move on to the next lecture next time. So hope this will fit your criteria, right? Okay.